Hi everyone, I'm Zhipeng from University of Texas at Austin. Today I present my work, Boki, Stateful Service Computing with Shared Logs. In today's cloud computing, service computing is a popular paradigm. Cloud provider offers function as a service, or FaaS. The user simply invokes their cloud functions that execute on cloud provider's infrastructures. For stateless functions, FaaS is easy to use and highly elastic. It can easily support thousands of concurrent functions. However, storage becomes more complicated when functions are stateful. Cloud providers offer various kinds of storage services for serverless functions to store their state. For stateful functions running on FaaS, they interact with these external storage services for maintaining their state. In reality, service applications often compose multiple functions. For example, service workflows. These functions can concurrently access and update states maintained in external storage services. Also, each function can fail during their execution, potentially leaving inconsistent state in the database. So that, in general, state consistency with fault tolerance is actually very difficult with the current infrastructure. Now let's consider an example. Here is a conference registration app using a service workflow. Suppose I'm going to register for SOSP using this app. It first has a function X responsible for creating a profile for me. It first generates a new user ID for me by using read and incremental operations with database. Then it writes my name to the profile table with the user ID as a key. Then function X invokes another function Y, which is responsible for adding my user ID to the attendance list of the conference. Function Y is invoked with user ID and it makes append list updates with conference table. However, failures can happen in different places. The failure can happen in the middle of function X, in between two database statements. The failure can also happen when invoking function Y. In this case, the function Y is actually not invoked. In both cases, data stored in the cloud database can be inconsistent. For example, my profile is created, but my ID is not added to the attendance list. So when such failure happens, the workflow is restarted, and there's no easy way to detect and fix the inconsistency problem. A common solution for this kind of problem is log-based mechanism for fault tolerance, for example, red hat logging. And the shared log can actually be used as storage media for red hat logging. In this approach, all operations are logged before executed, including database operations and also function invocation operations. So with such a log, when failure happens, the workflow can inspect the log to understand its progress and respond accordingly. For example, they can skip finish operations and redo unfinished operations. Besides red hat logging, we can actually have another service use pattern of shared log. Consider applications that consisting concurrently running functions and how to maintain a shared state between them. We have a classical wisdom state machine replication in distributed systems, and the shared log can actually provide the storage media for SMR. In this case, function XY will append state machine commands to the shared log. They can append concurrently, and the log will order these commands. Later, function XYZ they read back commands from the log. They will all have to read the same sequence of commands, so that shared state machine can be reconstructed by applying these commands in sequence. We can see in this example, the total order provided by the shared log is actually the source of consistency. Now, this is our proposed system Boki, which is a FaaS plus shared logs plus support libraries. We start from a FaaS runtime for executing serverless functions. We use Nightcall, one of our previous works. Nightcall is a low latency FaaS runtime optimizing for microservices. Then we add shared logs. These two components compose Boki's underlying runtime. Boki export a LogBook API for serverless functions to use these shared logs. On top of the LogBook API, we build support libraries to simplify the usage of Boki shared logs. Serverless applications can choose to link with these support libraries. Now let's start with the user-facing LogBook API. A logbook is essentially an append-only log. Every record in the log has a user-provided data payload field. Log records has unique monotonic sequence number representing their position in the log. Also, each log record has a set of tags, potentially empty. Tag is used for selective reads. LogBook's read API allows providing a tag so that its read will only consider records having the given tag. In this sense, records with the same tag will form a logical substring within a logbook. This feature is important for specific shared log use cases. In Boki, every function invocation is associated with a logbook. For service application composing multiple functions, their functions will associate to the same logbook. In this case, the shared logbook can be used for managing states between functions with consistency and fault tolerance. Next, let's dig into Boki's internal shared log designs. Where we have many previous excellent designs of shared logs, but serverless environment actually create new challenges for Boki. Specifically, the serverless environment requires Boki to efficiently support diverse use patterns of shared logs. We want high throughput because our shared log system can achieve append throughput more than 1 million appends per second. And Boki must provide this level of performance for application require it. We also want low latency. The serverless environment uses disaggregated machines for compute and storage, so that low latency reads can only be achieved by caching data on compute nodes. In this case, Boki has to address the issue of read consistency. We also want high density. In the serverless setup, a large amount of applications will only use a small amount of resources, and Boki has to efficiently support high density of small logbooks so that minimal metadata overheads are associated with individual logbook. Boki design actually including novel techniques to address these new challenges. Boki used multiplexing to achieve high density. Many logbooks are multiplexed over a fixed number of internal physical shared logs. And Boki built log indexes of these physical logs to allow flexible logbook reads. For low latency, Boki co-locates log index with functionals and build record caches on the functionals as well. Finally, Boki has an interesting Metalog design that jointly addresses log ordering with high throughput, read consistency given index and caches, and most importantly, the Metalog bridge different Boki components together as a fault-tolerant distributed system. So let's start with the first technique. In Boki, Boki's internal physical logs are distributed shared logs with high throughput. And for application level logbooks, each logbook maps to a physical log. So appending to a logbook translates to appending to the associated physical log. So in this case, logbooks actually multiplex over internal physical logs. And in the example, logbooks A and D are multiplexed on physical log 1, while logbooks B, C, E are multiplexed on physical log 2. And Boki is configured with a fixed number of physical logs, but can support a high density of logbooks. In order to achieve high throughput, Boki's physical logs are sharded. Each log shard is stored on 3 storage nodes for fault tolerance. And each log shard makes its own progress. And there is another sequencer for ordering log records across different shards to form a global totally ordered log. And Boki uses ScaleLog's high throughput log ordering protocols. Now we see that in the physical view, Boki's shared log is a mixture of log shards. But from the side of applications, the logical view is that many different logbooks are multiplexed over a single Boki log. So the question is how the logical view connects to the physical view within a Boki log. We have an initial idea that to assign every logbook to some fixed log shard, this design will simplify LogBook Reads because there is a fixed relationship between the two. However, this design has an obvious drawback that the throughput of a logbook will be limited to a single shard. In Boki, we want records from a logbook can go to any shard so that a logbook can enjoy the full throughput provided by the underlying physical log. In this approach, the challenge will become how to locate records for LogBook reads because there's no fixed relationships between logbooks and log shards. So Boki actually built log index to locate records for LogBook reads. Given the semantics of LogBook reads, Boki built log index which group records by book ID and tag. For each pair of book ID and tag, the index maintains a sorted list of sequence numbers for matched records. So for LogBook read, we first find the corresponding index row and performing binary search in the sequence number list to find the sequence number of the result record. Finally, we read the records from the storage nodes. Boki's log index will only include metadata of log records, including sequence numbers, tags, log book IDs, and which shard contains every record. So the index will have very small per record footprint, and a single machine can actually maintain the full index for an entire physical log. So then we will see for low latency reads, Boki co-locate log index with functions, while also cache log records on functionals as well. Here's an example of a functional for executing serverless functions. Functions are executing within function containers, and Boki has many functionals of this kind. On each of the functionals, Boki runs a logbook engine process for handling logbook API requests from the functions. Then the logbook engine actually builds and maintains the previous mentioned log index. Also, the logbook engine also cache log records by their unique sequence numbers, so that for logbook reads, when we know the sequence number of the result record from the index, the local cache will be checked first. If the record is not cached, then they will read the data from storage nodes. So with this kind of design, it means that in the best case, logbook reads can be served without leaving the function nodes at all. So in Boki, we have multiple physical logs, and for each of the function nodes, its logbook engine will only maintain log indexes for a subset of physical logs instead of all physical logs. On the other hand, a physical log will have many logbook engines maintaining its index for read scalability. So in this case, for a logbook read, the local log index may not be able to serve these reads, and it has to use index from another logbook engines on other function nodes. To allow maximum flexibility, we want a log read can be served by an index of the by any index of the target physical log. But how can we ensure read consistency given multiple copies of log indexes? For the shared log abstraction to be useful, consistency and the strong consistency is actually very important. The shared log abstraction requires very strong read consistency, for example, read or writes and mononotic reads. Finally, we discuss Boki's interesting Metalog design that actually orders log records with high throughput, ensure the read consistency given we have multiple copies of log index, and also achieve fault tolerance for the entire system. Because that a Boki log is sharded, log shards are stored on storage nodes, and there's another sequencer for ordering records between shards. The Metalog is stored and appended by the sequencer for the purpose of log ordering. To order records across shards, Boki use scale logs protocol. In a high-level scale logs protocol, periodically issue cut vectors to form a totally order across different shards. And sequencer maintains this Metalog that including issued cut vectors. And the Metalog is also replicated to another sequence node for fault tolerance. So then we know that actually for every cut vector in the Metalog, it essentially adds a new batch of records to the global physical log. In order to build log index, logbook engines actually subscribe to Metalog to learn the progress of the physical log. Then the index is built incrementally in accordance with the Metalog. When a new Metalog entry is read by the logbook engine, it adds a new batch of the record to the index by reading their metadata from storage node. Now we know Metalog actually corresponding to cuts in the physical log, and Boki actually use Metalog position to provide read consistency. So we have multiple copies of log index maintained by different logbook engines. The indexing progress is in accordance with the Metalog. Actually, different replicas of index make their own progress totally independently, so that they actually consist inconsistent data to each other. However, like Boki can achieve read consistency from the reader side, Boki maintain Metalog position for log readers, which are serverless functions in our case. The maintained Metalog position indicates the log reader's observed states to the log. For example, function f starts with the Metalog position 0, indicating it has not observed any states regarding this global log. Then function f reads record x via index b. After the read, the Metalog position of function f is updated to be the same as index b, which is 3. Then for later log reads, Boki performs consistent check using functions Metalog position against the index. For example, if function f wants to read from another index a, the consistent check will fail because reading from a could violate mononotic reads. We can see in this case, function f has already observed record x, but index a does not include this record. Similarly, when appending a new record to the log, the Metalog position of the function is also updated. In this example, function f appends record y to the log, and its Metalog position is updated to 4 to ensure read or write for future reads. Finally, we'll see the Metalog is also an important part of Boki's fault-tolerant mechanism. Recall that the sequencer maintains a Metalog used for log ordering, and there is actually another backup sequences replicating this Metalog. Boki has a control plan for failure detection. Boki uses reconfiguration to handle failures, meaning to set up a new arrangement of nodes for every component. So when no failures happens, the control plan first detects the failure and then initiate the reconfiguration protocol. Intuitively, the Metalog controls the global progress of a physical log. Because the Metalog orders records between different shards and the index are built following Metalog progress. So stopping the progress of the Metalog will stop the progress of the entire system. When everything is stopped, the control plan can easily set up a new configuration with safety. Therefore, the next step is to seal the Metalog with all sequencers. A sealed Metalog can no longer has new entries appended. Boki uses Dallas log sealing protocols, which can handle the case that some sequencer has failed. When the protocol is successfully finished, the Metalog is sealed. Because the Metalog is sealed, every parts in the system are frozen. So at this moment, the control plan can safely set up a new configuration. And in the new configuration, a new Metalog is used. The last piece in Boki's architecture is the support libraries. We built 3 support libraries for 3 different serverless use cases. The first library we built is BokiFlow, which provides fault-tolerant serverless workflows. BokiFlow allows composing stateful functions to form a workflow while providing strong end-to-end guarantees, for example, exactly once execution semantics. The second library is BokiStore. BokiStore is a transactional object store for stateful functions. It provides objects and a model as JSON objects. BokiStore achieves strong consistency and provides transaction support. The last library is BokiQueue, which provides high throughput message queues for serverless functions. BokiQueues enables message parsing and coordination between different functions. They all leverage well understood techniques, but still require some adoption to work with the LogBook API. This library provides very useful functionalities, but they are normally challenging to implement in a distributed setup. But actually, the shared log significantly simplify implementation of these libraries, where each of them only requires at most 1,200 lines of code. Then we conduct our experiments on AWS with EC2 VMs. For a physical log, there are 3 storage nodes storing each log shards, and there are 3 sequence nodes storing its Metalog. We start the evaluation by Microbenchmarks on logbook operations. For log appends, Boki can achieve high throughput. The append throughput can scale to 1.2 million appends per second. In this case, the median append latency is still low, which is around 2 milliseconds. Boki also achieves low read latencies. In the case that local log index is used with a cache hit, the read latency is as low as 120 microseconds. For other cases, the median read latencies are generally within 1 millisecond. Then we evaluate how Boki supports realistic serverless workloads. We start by comparing BokiFlow with Beldi on serverless workflows. We have 3 comparison targets. Unsafe baseline has no mechanism for fault tolerance, so that the state can be inconsistent on the workflow failures. And Beldi builds a uses log-based protocols for fault tolerance, but it builds a logging layer over cloud database DynamoDB. BokiFlow leverages Beldi's techniques, but using logbooks as a logging layer to implement their techniques. Here's the results of microbenchmarks on Beldi's primitive operations. We can see that for all operations, BokiFlow has significantly lower latency compared to Beldi. This justifies Boki can actually provide a more performant logging layer to support Beldi's fault-tolerant protocols. Then in the benchmark realistic workflows, BokiFlow significantly speed up the end-to-end execution time while providing the same strong guarantees as Beldi. BokiFlow can speed up the median execution time up to 0.7x. Then we evaluate BokiStore. We compare BokiStore with MongoDB using a Twitter clone workloads. For throughput, we see BokiStore is up to 25% higher. Then we break down latency by request tabs. For single shot read requests, for example, user login and user profile, BokiStore is slower than MongoDB. However, for transactions, BokiStore is significantly faster. This demonstrates the strength of log structure storage. Finally, we evaluate BokiQueue. We compare BokiQueue with Amazon Simple Queue Service and Apache Pulsar. We test various setup of producer consumer functions. For message throughput, in every setup, BokiQueue has higher throughput. Also, for all the tested setup, BokiQueue has the lowest message delivery latencies. Conclusion: Boki justifies the value of shared logs in stateful serverless, where shared logs can provide mechanisms for consistency and fault tolerance. Boki proposed novel shared log techniques to address unique challenges introduced by the serverless environment. Boki support libraries demonstrate how shared logs can support 3 different serverless use cases. An evaluation of these libraries shows that Boki can speed up important serverless workloads by up to 4.7x. Finally, Boki is open source on GitHub. Thanks very much for listening.